All right. Well, so thank you very much to all the panelists who have come here for this first panel discussion. I'm going to moderate it, and I'm going to wing it as best as I can right now. Okay, so we have 5 folks. So Ashwin, Sampath, starting there, from Qualcomm, Tim Thomas from Nokia-Bell Labs, Wong from National Instruments, Sadri from Intel, and Maziar Nekovee representing the 5G millimeter wave MMAGIC project. So what I'm going to do is going to start with all of you making an initial 2-3 minutes remarks on where you see in terms of the state of millimeter wave technology and key challenges and opportunities, both from an industrial and regulatory aspect, and then we'll move from there. I'll ask some questions, and then eventually, hopefully, we'll have a lot of audience involvement here as well. And I think we should have one mic for the audience somewhere too, right? Okay. All right. So let's start with Ashwin.
Okay, hear me? Okay. First of all, it's a great pleasure to be here, and thanks, Akbar, for inviting me. It's an honor to be on this panel with my colleagues here. So giving a 3-minute introduction is a little bit challenging. 3 minutes seems like a long enough time. So forgive me, I wrote down a few points that I'd like to use as talking points so that I don't ramble on aimlessly. So let's see where we are in terms of our understanding of millimeter wave. So the way I'm going to talk for the next few minutes is what we know about millimeter wave, its characteristics, devices in particular, which is of great interest to me, and some of the solutions that people are talking about. So let's start with propagation, the most obvious thing which drives everything else. The notion that non-line of sight propagation is feasible with millimeter wave is now more or less accepted. Is it going to work in every single place? No. But can you sustain links in a non-line of sight manner? This seems to have been proven out by numerous measurements that people have made, including ourselves. Reflection as a primary mode of non-line of sight propagation seems to be the most likely. Diffracted paths tend to be extremely weak. In areas, urban areas where there is a greater probability of metallic reflections, could sustain non-line of sight links, and this has been also shown to be true with many of the results that people have published. Foliage continues to be a serious area of concern, especially in suburban areas and for the out-to-in use case that is being looked at. So that has to be carefully factored into the link budget. You cannot have a superb link in winter in the Northeast, only to find that as spring comes along, your data rate slowly fades to 0. So foliage and working around foliage really needs to be factored in, especially for out-to-in coverage. Delay spread. So the general feeling about delay spread is that, delay spread does tend to go down with beam forming on both ends, but does vary a lot. The radar cross-section effect comes into play, making smaller objects more visible. And so it's really a little bit of a mixed bag when it comes to delay spread. It really depends upon the scenario you are in. So a broad conclusion that delay spread may not be as significant an issue is a little bit difficult to paint in a broad way. Path loss exponents and shadowing aspects have been looked at. Our own measurements, which I must admit are in suburban parts of New Jersey, do indicate that the path loss exponents don't seem to be that different compared to the lower bands. One of the things that we did in our measurements was to actually do 2.9, 29, and 61 side by side, which means the same measurement at roughly the same time with the same equipment. So we had a nice way of actually comparing apples to apples, if you will. So that's the first piece of the puzzle, propagation. RF impairments is another aspect. As I said, device side of things is very important for in my personal interest. So in the past, in the sub-6 gigahertz systems, we didn't have to pay that much attention to things like phase noise. As you go higher in the bands, you have to start focusing more on phase noise, both from the circuit design perspective, as well as I'll say shortly, from the air interface support perspective. The second aspect is PA efficiency. The uplink continues to be a challenge that folks should pay careful attention to. So PA efficiencies and the associated power consumption at the mobile unit in order to achieve reasonable uplink link budgets is an important problem to solve, especially for CMOS PAs. And the third aspect is what is our notion of interference? Most air interfaces that we look at today, at least the cellular air interfaces, look at interference as an averaged effect. What I measure now holds when I schedule you. Will this continue to hold for a millimeter wave with the beamforming, or is your interference a strong function of who's being scheduled? And if so, what are the solutions for it? Now, moving on to some of the solutions and things that we need to look at on the air interface side. So fundamentally, everybody agrees that closed loop hybrid beamforming, which includes an analog beamforming component, is critical to close these links. So one of the interesting things here is how do you bootstrap the system? Which means that your initial search, even to discover the presence of a millimeter wave base station, has to be done in some intelligent way, potentially through some beam sweep. Any kind of broadcast signaling, common reference signals are expensive. They have to be repeated in multiple directions and so on and so forth. Similarly, reference signals for mobility need to be carefully thought through. How do I measure my neighbor? When do I know when to scan? What is his scan pattern? So on and so forth. And all of this has to be done. The link setup, bootstrapping, all of this has to be done in a closed loop manner to get into the system, and the link has to be maintained in this closed loop manner. The other aspect, as I alluded to earlier, was delay spreads. So the standards are looking at things like multiple subcarrier spacings and cyclic prefixes, unlike LTE, which had a single subcarrier spacing. So wider subcarrier spacings, good for phase noise, good for TDM scheduling, which is another important part of millimeter wave. If you're doing analog beamforming, you cannot FDM users that efficiently. So you'd like shorter symbols so you get resource granularity in time. So wider subcarrier spacing help from that perspective. On the other hand, it's obviously poorer for handling delay spreads. Reference signals for beam training and tracking need to be put in. In addition, you need to put in reference signals to compensate for things like phase noise, which might need active mitigation, especially for higher constellation sizes. And then there's always this debate of single carrier versus OFDM. The trade-offs are well understood. Single carrier has also some additional value in the case of millimeter wave as we operate in more link budget limited scenarios where the MIMO order may not be that critical, especially for the uplink. Device side, a bunch of challenges. As I talked about, the PA is an important aspect. Antenna module and placement is another very important aspect. Space is a premium on phones. However, we all use our hands to use these devices. So hand blocking becomes a critical issue. So how do we solve this? Do you place multiple modules in multiple locations in the phone? Do you have space for it? And then if the PAs are not so good, maybe you need to use many more elements to actually cover the uplink. And then it again comes down to cost and power consumption. And finally, on the deployment side, what we've noticed in all our experiments with our prototype system is that you need heavy overlap in coverage. It's not so much about whether your link budget is 150 meters or 175 meters. We like to talk in terms of a local link budget. For example, recent experiments, mobility experiments that we were doing with a minivan, a Honda Odyssey minivan, we found that depending on whether we were facing the base station from the front of the minivan or the back of the minivan, played a role a significant role in the performance. Propagation through the back window, through the back set of seats, to the front seat where the passenger is seated, tended to have higher attenuation, in which case having another base station reaching deep into the other cell seems like an important. So there's irregular cell shapes to deal with. And then finally, self-backhauling, which was alluded to earlier. I think we have a tendency in the cellular community, if you don't mind a minute of self-criticism, to leave the backhaul to be someone else's problem. Millimeter wave, in some sense, forces us to think about it more holistically. Backhaul is our problem. We have small cells. In order for this to be successful, we have to solve the backhaul for a problem in a seamless manner, integrating it to the same air interface if possible.
Thank you. So very well put. So I'm filling in for Amitava. You get to actually get to hear maybe a little different perspective. He's on a lot of panels. So from my perspective, industry, you can tell, is moving, I think, faster, a lot faster than research is going. The standardization process is moving very fast. They're already tackling below 40 in the study item, 40 gigahertz in the study item, and they're going to start in April taking up above 40, and this is in the 3GPP. That means that they're actually looking and making solutions, I think, without having all the answers yet. And a lot of the answers that are known yet are still in like the propagation area. So they did come up with a channel model, and it was based on quite a few measurements. In certain environments, though, they don't have a lot of measurements and they don't have a channel model. One is a very important environment, which is the suburban environment. So the suburban environment, especially in U.S. picture, like the homes, you have a lot of foliage, which was already alluded to, that the foliage is a big issue. Not so much this time of year, it's actually nice, but it's when the leaves are on the trees, they attenuate the higher frequencies more. That whole environment has not been tackled by 3GPP. And what that means then is they're going to come up with a solution that people are going to want to deploy there, but it's not really optimized for some of these other environments. The other aspect, of course, is Verizon is going full speed ahead on trials for the suburban area, and they're going to be learning kind of as they go along. They do, and I'm sure everyone knows this, that the specs are available. You could look at it. So they developed specs without really having all the answers, and the channel model, say, they used for that was really all based on, I know because I helped develop it, was on ray tracing. So you're relying on not having the measurements to really come up with a good model. So they're going to learn. So things like that, they're going to learn that. First thing they like something they wanted to deploy, they wanted to do it for wide ranges. And the first thing you learn, no, you can't do it for 1 kilometer cell radiuses. People are saying that from the beginning, and foliage plays an issue, blockage. And then the other big thing that was learned, and this is one thing that I think we do have a good handle on, is penetration loss. That once you go outdoor to indoor, you lose a lot of the signal, and unless you intelligently place the CPE. So either it's going to require the users to be aware of that and place the CPE in a good place, or you're going to have a truck roll, which is expensive, or on the outside of the house, which hopefully has a better characteristics. But all that too, you also need the backhaul to be able to support this. So we're already talking, say 200 meter cell radiuses at best. You got to have the small cell deployments. You got to have self backhauling, because again, every time an operator goes out and wants to deploy these, if they have to do a truck roll, that's very expensive. If they could just go out and place the units, have them all configure themselves, talk to each other, and do like a mesh backhaul, that would be perfect. And so millimeter wave is actually excellent at that, especially at the higher frequencies. Say when you get up around 70, because you have a lot of bandwidth, you do in-band backhaul, and so you basically have a system that kind of could do both the access and backhaul. So it's a natural progression. And don't think, again, millimeter wave just for backhaul for a millimeter wave system. It could be backhaul for even the massive MIMO system. There was a real good panel session a couple of days ago on what's better, below 5 gigahertz massive MIMO or millimeter wave, and really they're complementary. You could start off with millimeter wave being the backhaul and could evolve into being backhaul and also access. So I think there's going to be still plenty of challenges. There's still going to be challenges in how to point the beams, control channels. I think 3GPP and stuff is going to come up with solutions. Verizon obviously has, but I think there's going to be refinements for sure. And they might learn that, oh, maybe we need to track faster because we have a situation where just a truck driving by could block the main signal or it could reflect off it, and they didn't design for that higher speed case. So I think there's going to be a lot of things learned. There's also a lot to be learned in the propagation environments, and also the device side. What are the best for actually building the arrays? What are the best arrays that could be used at these various frequencies? And I think we pretty much covered on I think what I was going to say.
Hi, my name is Ian. I work for National Instruments. I know a lot of you. I kind of manage our wireless research group. I think I'm probably the only panelist here that's more on the test and measurement equipment side, and we also supply equipment for rapid prototyping. So we kind of have a unique perspective because we have a partnership with Nokia, supplying them equipment and doing their rapid prototyping, and also on the measurement channel sounding side with NYU and AT&T, for example. So, I mean, from my perspective, at least what I've been seeing as the biggest challenges for millimeter wave success, right? Ultimately, we're all in this research area. A lot of you are academics. You want this to be a commercial success. So, given that I only have 3 minutes, I thought of kind of four P's for success. Okay, 4 P's. So thinking propagation, protocol, performance per watt, performance over power, and price per performance, price per MIPS in a way. So in propagation, I think one of the biggest challenges, and Tim alluded to this, is we are like at the infancy of understanding the channel. We have some good work by pioneering research that some of you are here that are doing, but if you think about it, sub-6 gigahertz, some people think that we've solved it. People are still doing channel measurements on sub-6 gigahertz and understanding more and more things about it. So we're at the infancy of it. We need some more innovative channel sounding techniques. So it's not as simple as just path loss models, right? We need to be able to understand what is a phased array in these types of environments. How does that affect the channel? I mean, we're learning a lot already. We're starting to build protocols around it, but I think there are innovative ways on how to do channel sounding and channel measurement, and I think there's some innovative thinking can go in there. On the protocol side, I guess coming after you guys is a bit hard to kind of add even more things to it, but one thing that I did not hear a lot about is hybrid beamforming. So I think it's kind of one of those. I mean, Verizon 5G spec is kind of built in to do hybrid beamforming. It's basically the mix of analog and digital is very important. We actually have that in sub-6 gigahertz in the form of FD MIMO for massive MIMO, but for millimeter wave it's almost required, right? Because of the large bandwidths, and it's going to be prohibitive to put. I mean, we know massive MIMO gives us a lot of benefits, but we can't really put 128 transceivers each at 2 gigahertz of bandwidth up on a base station. It's probably going to be cost prohibitive, at least for a few years, right? Until someone here does a breakthrough on making that really cost efficient. So that's kind of one thing I want to bring out. Like, we need to understand the right protocol. How do we do the right levels of CSI feedback? How do we do the really truly lower the latency? So the Verizon 5G spec is built for fixed wireless access. If you look at the way the beamforming kind of reference signals are put there, it's actually pretty slow. It's really meant for stationary customer premise equipment to kind of a base station type of protocol. So a lot of things need to be understood for enabling true mobility, which you all know that's when it becomes a commercial success. I do want to point out the nice insight Ashwin said about the van, kind of where it is and kind of inside outside. I think some of you may remember in LTE there's a lot of work on COMP, right? Cooperative multipoint. It sounded really cool. People started putting a lot of effort into it. I don't think that's really much deployed right now. I mean, because the nice thing about sub-6 gigahertz is there's enough propagation multipath that you can get a lot of diversity out of MIMO channels. But for millimeter wave, I think the ability for base stations to cooperate becomes almost a necessity for even a sustainable link. So I think that's pretty important. So that's kind of my wheelhouse, more on the propagation protocol side. But I think there's a lot of folks here that are doing kind of the devices, right? Ultimately, we need to put them on the handset. Is it RF CMOS? Is it SIGI? And whatnot, to make sure that we can actually, ultimately the success will come from low enough power on a handset with the right cost. And I think that's really important. On the architecture side, so we also work with a lot of people who are prototyping millimeter wave access links today. How do you move data around, right? Like, what is the right architecture? Today in 4G, there's this kind of canonical remote radio head with RF filters, a baseband at the bottom of the base station, connected via CPRI, and then a backhaul link fiber or even some wireless. I think we need to rethink how we even put the different layers into that whole kind of end-to-end, from core network to the edge to the radio. Like, where should we put processing so that it's cost-effective, it's not expensive, we don't need 100 fiber links and whatnot, right? So I think these are things we need to think about, and maybe there's some flexibility that needs to be built in, right? Like Cloud RAN is probably good for still the typical data use case, not super low latency because you kind of hit the latency, but cost is down. But for low latency, ultra reliability, you probably need to put a lot of processing, a lot of the PHY on the edge, and so on. So a lot of things to think about, and yeah, I'll stop it at that. So.
Okay, I guess you can hear it. Thank you very much, Akbar, for arranging the event. Very glad to be here. My name is Ali Sadri. I've been with Intel for past 15 years. I run the millimeter wave standardization and advanced development. In my past life, I founded the WiGig Alliance, and back in 2008, and about 2013 we merged with Wi-Fi Alliance. There have been a lot of great discussions here about some of the features of the millimeter wave, and we do have some background on at least in 60 gigahertz that we started back in 2008 as well. And in terms of commercialization, I think it was somewhat a success. I think this year you will see more products based on WiGig standards or 11AD out in the market. And from this experience, we actually learned a lot. And there's a lot of things that we know, and there are a few things that we don't know. I think we know how to do beamforming. I think we know how to build the silicon, how to build the phase array. We know which modulation is more suitable for certain applications and so forth. And I can probably pinpoint to one outstanding issue that we still need to resolve, which is beam tracking and mobility. And I think that's one of the things that, it was mentioned by my colleague as well, that the Verizon, they're smart enough that they looked at the first deployments of the millimeter wave technology as to be a fixed access. And that's not coincident. I think tracking of a mobile device at the millimeter wave frequency is quite challenging. I think based on at least what we learned so far, we have another 10 years to learn that. So the foreseeable future, I think we're going to see fixed access in millimeter wave frequencies. And when we talk about millimeter wave frequencies, anything over 30 to 100, I would consider it quite similar. And 28, I would call it 30 as well. And in terms of propagation, in terms of modulation techniques, in terms of the beamforming, I think the challenges are quite similar. Maybe the transmit power EIRP is slightly different from one frequency to the other. But in terms of the usage models and the range of the transmission, a couple of 100 meters, we can sort of like summarize all of them into the same bucket. And I don't think that there will be any surprise. For example, a 28 gigahertz system within a couple of 100 meters, performs drastically better than the 70 or 60 or 40. I think they will behave quite similar. And these are things that we'll learn. As I mentioned, one outstanding issue is tracking and mobility. That remains a good challenge for both research and the industry to figure it out. Thanks.
Thank you very much. My name is Maziar Nekovee. I'm currently responsible for Samsung's European 5G research and collaborations. And I'm also the coordinator of a project called mmMAGIC, a European project co-funded by AEC, which is coordinated by Samsung, and Ericsson is technical manager, Intel, Huawei, Nokia, and also 2 major operators, as well as some of the major European institutes, research institutes are part of it. And this project is focusing entirely on millimeter wave communication for 5G, including all the components, channel models, architecture, radio interface, and so on. I'm delighted to thank Akbar and the organizing committee that invited us, my colleague, and also Dr. Honukumbore there, and Professor Tommy Svensson, to be a sort of a bridging between Europe and US in this area. So we hope to be able to fulfill this. So just a few thoughts now, and then tomorrow there will be more discussions and poster we have that will go into details of mmMAGIC. In terms of challenges, I think our colleague from Qualcomm was NI. Both mentioned the sort of industry activities that are happening here. So obviously 3GPP moving fast. We expect the phase 1 of 5G to be ready, released in mid-2018. That would include the NR, also higher frequency above 6 gigahertz, and then phase 2 to be finalized by 2019. So some of the aspects of millimeter wave, such as physical layer and some of the hybrid beamforming and even channel model has been already addressed in 3GPP, although there are some remaining issues. That channel model was maybe, for example, if you want to look at the deployment by operators, you need map-based channel models. In mmMAGIC, we have just released our own channel model software, which is the result of very massive, about 10,000 measurements across Europe in 5 European countries. And this is looking at new aspects such as diffusive component, such as blockage models, such as ground reflection that need to be also included. So you're very welcome to download that. So I think, but there are new challenges in millimeter wave, and these are a bit more related to actual deployment by operators. I just came from an event in Brussels where the European Technology Platform has organized it, and there's a figure of 600 million euros investment that the European operator need to do in 5G. Now, I'm not sure if it includes some of the requirements for millimeter wave. And these requirements, one of them that I think is very important is, as we know, in millimeter wave, one of the issues that we can have patchy coverage. Therefore, the concept of cells is not very well defined, and collaboration between multiple base stations, so network collaboration is extremely important in order to enable a very smooth coverage. I must mention that Samsung has already done, and we announced this demonstration of handover between 2 millimeter wave base stations at quite a reasonable speeds. So I think there is challenges there, but they are solvable. Therefore, a lot of challenges remaining for millimeter wave, in my view, are related to deployment by operators in the future and operation. One of them that comes to mind is that, as also a colleague from NI mentioned, that in terms of architecture, CRAN versus DRAN, the European operators' roadmap is to move to CRAN, which means that you have remote radio heads and basically using that. But when it comes to millimeter wave, and we have just about to finish a study in mmMAGIC on techno-economical aspect of it with 2 European operators. If you consider a CRAN architecture for millimeter wave, depending on functional split between the BBU and remote radio heads, the data rates that would be required for CRAN could be much higher, around 100 gigahertz at least or higher. And the question is then, how can you actually cater for that sort of CRAN architecture? So I think this is a very interesting area to see if we can come up with wireless solution, maybe at even higher frequencies. The other aspect is in terms of a management of millimeter wave systems, how this can be done. Things like self-organizing networks, obviously self-organizing networks themselves are not going to be standardized in 3GPP, but all the signaling and so on that would be required, this has to be in the standards. And I think think millimeter wave is a great area, given also the high densification. The FCC speaker mentioned that we are going an order of magnitude higher number of base station. So self-organization is an extremely important area, and for millimeter wave is even more important because we have this new resource, the beam, that also need to be self-organized. So that's also thoughts from my side, and we are here until tomorrow, and we have our first annual report, so I also provided here, and if you're interested, you could email me and get some more info on mmMAGIC. So thank you very much.
See if this is working. Yeah. Well, thank you for your introductory comments. Let's see. So I was surprised. I heard a lot about channel propagation and beam steering and some of the hardware challenges. So I'm just going to ask a couple of questions, and then I'm going to get the audience involved a little more too. One of the things that I didn't hear about is the networking or other aspects. When we look at millisecond latency, for example, it seems to me that there's going to be a lot of changes at the back end and the networking layer too. Any thoughts on that? And the second part is power consumption. I think there's a lot of processing going on, and so is there anything on that front that you guys can shed some light on?
A networking guy rather than RF. In terms of latencies, obviously this is an interesting area, and it also comes to the architecture. Mobile edge computing solutions comes to mind. That is something that industry very much considering to reduce the end-to-end latencies, also millimeter wave. I think that's an interesting area as part of architecture. The other thing you mentioned networking, and I would say that also the interaction with the physical layer and TCP and higher layers is very important. It's already well known that LTE, for example, with TCP could be very spectrum inefficient. Therefore, and we are doing some recent research at Samsung to look at, are there ways to improve this feedback loop between TCP and the lower layers, because even if you get millisecond latencies on the physical and MAC layer, because of the TCP low start, you may get, increasing latencies. So how can we do things like network coding, or maybe some other codings, or altogether, the split of TCP when it comes to millimeter wave.
So maybe I touched the power consumption issue. I actually don't look at the power. I looked at the energy. Power, obviously, at any instance could be high, but during that instance, how much bits are you transmitting? So in terms of the energy, if you compare, at least looking at the WiGig and 7 gigabits per second, comparing to maybe the traditional Wi-Fi, you're a lot more, I would say, energy efficient, at higher transmission rate, or even at 60 gigahertz comparing to the lower frequency. But having said that, you need to make sure that your utilization is such that you transmit the bits and then you go into the sleep mode, and that's how you kind of like average down even the total energy. For example, majority of the discussions on the fixed access, let's say, even with the 28 gigahertz, they're looking at gigabit per second transmission at the receive side. But if the 5 can, for example, transmit 3 gigabits per second, then about a third of the time you're in sleep mode. So I think that looking at all these combinations of the utilization of the system, I think the total energy in general is less at these large bands and higher frequency.
Well, I was just going to add that that's the transmission. What about the computational power? Because there's a lot more computation happening. And
it depends how you implement it. At today's technology, majority of the beamforming is done in analog, right? So until Ali comes with a digital beamformer, I think we're going to stay in analog world for a long time, and the digital side is not computational intensive, actually. It's a single carrier modulation with some sort of coding, whether LDBC or not. But the analog side, I must say, yes, it consumes a lot more power than the digital side.
I was going to add to the first one, the architecture of the system and the way millimeter wave propagates is going to impact how you have to design things and move the data around. One thing is if we want to keep the latency low, if you get blocked to your desired link, you need to have another path that you could rapidly go around, and that could be to another base station. So this information that the stream going to the user can't just be at one base station. It's got to get to multiple base stations. That's a huge backhaul problem, too. And then for the power consumption, I think obviously it'd be nice to get the analog to digital conversion, to get the power of that down. But barring that, there's probably a lot of openings in the low bit ADC type area. And I think that could be one certainly area for algorithms to develop in the meantime that you get like a full digital stream behind each antenna, and that would be a huge game changer.
I agree with a lot of what Tim said, actually. So on the latency and architecture front, I think one thing, we need the network to be very nimble. If you're doing beamforming and tracking across multiple base stations, and you need to actually switch quickly, one approach could be to actually move some of that control down to the lower layers as opposed to treat it as though it would be a traditional handoff going into the network. This also involves as Tim said, the data to be disseminated in some, either cache or in some intelligent way proactively distributed. On the power consumption side, I guess there are multiple things that you could do. On the RX side, one thing that we do need to avoid is if you're inherently millimeter wave is very spotty, you don't want to be spending a lot of your RX cycles in searching constantly for the presence of the link. So this can be done through some waveform optimizations within the millimeter wave framework, but could also be done in the presence of an anchor link, like a sub-6 gigahertz anchor link. The other way in which you can do it is you don't mandate that the maximum bandwidth is processed all the time. So you have a hierarchical way in which you can actually open up the bandwidth so that both the RF bandwidth and the digital part of it. And on the digital side, I kind of agree with what Ali said. It doesn't appear to be a very significant, at least significantly different from a millimeter wave perspective. Control complexity should not be mistaken for overall digital complexity.
Okay, well, so in my big questions, there were, some like, are there any big breakthroughs? So I didn't hear anything, so that means there are no major breakthroughs that are here to report. So when do we think our first, it's going to be fixed wireless, everyone agrees. So when do we think it's going to be deployed and functional? 2 years time frame, 3 years time frame, when? Does anyone have any idea?
Well, I don't want to speak for the vendors that aren't here, but at least according to the plans, it's pretty aggressive, right? 2017, 2018 time frame. So very close in, and it's intended to be a pre-5G standard, right? It will be a good playground. They are taking the risk, which is good for the industry, and we will learn a lot. But yeah, I think it's 2017, 2018 is what I've heard. I don't know.
Yeah, confirm. I mean, that's the Verizon pre-standard type trials, and certainly by the time KT for the 2018 Winter Olympics will have a nice trial system. Again, these are more to demonstrate the technology, but I think they're going to have form factors too. It may not be perfect, but right, small. So Yeah, and of course, that'll be at the lower frequency. That'll be like at lower frequencies, 28.
Yeah,
28, 39, but not the higher frequencies would be later.
So let me give you a little legacy information. So as I mentioned, mmAGIC Alliance was formed in 2008. By 2011, 12, we were done with the specification. This is 2016, and we keep saying that next year is the year of deployments, which I think it is, actually. Next year it is, 2017-18. So having said that, we're dealing with somewhat simpler environment, which is an indoor environment. Outdoor environment is a different beast by itself. So when you ask when is the reasonable time for deployment, or when is the reasonable time for massive deployment? Deployment, Olympic is the deployment, right? So this is probably the first time that technology is tied into sports. But I don't believe that we're going to see massive deployments. This is not my company's, position, but myself, for next 10 years.
Well, that's interesting. Yes,
Also from Samsung.
Europe is
Obviously the fixed wireless access, and if you were in Globecom, it seems that companies such as Samsung pioneered this, but that there is no, and I was discussing to colleagues from Nokia, Huawei, that this is considered as the most viable 5G or pre-5G that is going to fly. The deployment would be in sort of 2018 time scale, and with backing from operators, we are confident this is going to be a sort of a very large-scale deployment. Now, bear in mind that the fixed wireless access use case, you have indoor CPEs rather than terminals, and then distribution initially has to be done with Wi-Fi. Therefore, the form factor, although companies such as Samsung, we are working very hard on also on form factor and pack it into terminals, but initially it will be CPEs inside the homes. So we are very confident that, just in Europe, I think also there are great opportunities. As I mentioned to you, there was this event that that Europe is very much also has the same questions, although some of the topologies are different in terms of coverage, bringing fiber to homes. That's too expensive. Therefore, there are also interesting opportunities there, and obviously we have also Korea and so on. So I think the path is really open, and there's also a very surprising industry consensus, as far as I can see, that this is going to be the first deployment pre-standards but commercial of 5G.
Let me add another, and this is my last question.
Let me challenge my friend.
Well, okay. Well, we don't want to duel.
No, one second. Is it deployment or massive deployment? Yeah, are we talking about tens of millions or hundreds of millions?
I think.
Thank you.
Okay,
and I think he answered my question.
I agree. I saw that it was a difference, a qualified answer. But Tim, I think, was mentioning the standardization is slower. Technology is going faster. Verizon is saying, hey, we're going to deploy. So do we see a problem with the standards creating a straitjacket, or are they going to be flexible enough? Do we have any idea on that? Could that cause a potential problem going forward or not? Maybe Tim, you can comment on that.
These answers we'll find out, but I think it's going to. I mean, one of the problems is what's the easiest thing to do as you move forward? Well, LTE already has a control design. They already have an acquisition design. So let's just reuse it. Verizon certainly very much followed the LTE design. The only difference was, you have beams. So instead of having it sent once out of like a broad signal, you're sending it multiple times out of little beams. But is that the best? Well, it was expediency. So I think that is going to be problematic, and I think there's better solutions, and there are mechanisms to fix that, but
hopefully maybe standards would hopefully evolve. They'd be flexible enough.
Yeah, and maybe when we go up to higher frequencies, maybe they'd be open-minded, but they tend to be the politics of it tends to be.
Just to add to what Tim said, at this point, if you look at where 3GPP NR stands, there's still a whole lot of room to play around with. They've been very mindful of the fact that, in fact, the mantra really is forward compatibility. They don't want to put things in a straitjacket, fix things to the point where adding stuff later on becomes difficult. Now the question is, how efficient are you in actually speccing something if you have this forward compatibility lurking on top of your head? So that remains to be seen.
Excellent. Okay, so now any questions from the audience for the panelists? Okay, let's read.
Thank you. So I'm Maitri Hunukumbura from Samsung and also from mmMAGIC project. So I'd like to ask the panel, like most of the applications you talked are like extreme broadband, typical cellular applications or wireless applications. How do you see the millimeter wave community working with other verticals maybe in the longer term, maybe in the mid-term, to exploit some of the opportunities there?
Yeah, I mean, I can add a little bit. I think one of the verticals that millimeter wave has a good potential for, and I see Robert Heath here, is on the automotive space. I think that, as you know, there's 77 gigahertz automotive radar. There's a lot of things to be said about the SRC and 802.11p on the improvements that can be done there. I think adopting millimeter wave and V2X types of technologies, I think that's a ripe, I wouldn't say ripe, but it's a potential area for millimeter wave to also provide some disruption into a fairly slow moving automotive industry, but it took them 15 years to adopt 802.11p. But let's see, hopefully it won't be 15 years before they adopt millimeter wave technology for cars.
I think specifically we're not talking about 28 gigahertz, so that was a good question you were asking. Millimeter wave goes multiple frequencies. I think there are some serious look at using 60 and 70 gigahertz for radar and imaging. I think Robert is also getting involved into that area as well as the virtual reality. I think these are the applications that we could most likely see in the consumer applications, consumer goods, cameras or whatever. But when we go to wideband and the 28 gigahertz and so forth, that's most likely only data transmission for the broadband side. It's a different usage model. But also the driverless cars, for example, those can benefit from it as well. Once you deploy these massive number of the access points or small cells, even the 28 gigahertz could play a role into communicating with these cars. Because the footprints of these access points or small base stations, they're within a couple of 100 meters. So it's the best way to control the cars. And especially if you have some sort of caching at each node, your interactions with the other cars and the control plane will be a lot faster. So I think there's a lot of use cases, but we got to go through this revolution of changing behavior. I mean, the cars are not going to suddenly become smart tomorrow. Life cycle for the cars, at least in developing countries, is about 10 years. And I keep saying it's 10 years, sorry for saying that, but that's the cycle that people get used to new devices and new applications.
Yeah, I mean, in Europe, obviously, this vertical application is extremely important because also to incentivize investment in 5G for Europe is very important to be able to do that. One area that is very interesting, and it's a great white paper by 5G PPP on this, is this what is now known as the Industry 4.0. So basically the penetration of digitalization of factory of the futures and so on. And one area that has been specifically mentioned is, this automated robots in industry, in the factories, and I think millimeter wave is ideal for that. So it gets a virtual reality control of robots and hazardous systems. Now, from technical perspective, that's very interesting because the scenario that you see, and you see that also with self-driving is this actually uplink transmission. So you can imagine that you have these robots and so on in a factory, and they send using 360-degree cameras or virtual reality camera the images uplink, for example, and then the remote monitoring system has to then send the feedback very quickly downlink to them. So the other interesting aspect is the uplink, but it's also a case of indoor usage. So it ties very nice, I think, with this fixed wireless access, because you can imagine that same sort of base station could be then used also in factories. So that's what comes to mind. But vertical is definitely extremely important for Europe, and I think there's a recognition also because we're working also with China, with 4G Americas and so on, that this is an area of interest, and also for millimeter wave, definitely when it comes to Israel.
I have a different question. I think John pointed out that you're going to have lots of cell sites that will need to be put up in order to have this kind of small form factor, small millimeter wave deployments. But based on what I see, there are two big challenges: form factor and cost. What is your estimate on when those two factors will be addressed or scaled?
Well, it's easy for me because we don't build the devices. We we test them and we give you prototyping equipment to kind of figure that out. But I think that'll be a good question for our colleagues, Intel and Qualcomm here on how we can. But I think as they mentioned, I think the WiGig experience has taught us a lot of things and gives us a bit more confidence on how to do this. And the fixed wireless as the first kind of test case does not need the level of multi-base station cooperation, I think, as compared to a true mobile. You're not turning your CPE around your head. At least most people don't. So I think that gives us some leeway to understand a bit better, to kind of then over time drive the cost down of both computation and the beamforming, and our folks here on the chips and architecture side will definitely have some innovative ideas to kind of drive that down. I think it's not an infeasible problem, let's put it that way. I think ultimately economies of scale will kick in, and we will learn how to do it in a low-cost fashion, and we've done it multiple times over in different generations. So at least from my perspective, I don't feel that that's a big showstopper.
Did you mean form factor for a mobile device? You're talking about the base station, then maybe Nokia should answer.
Yeah, I'm talking about base stations. So if you're going to put these things up, we have seen the recent demos. They're like this tall, the 6-7 feet tall units with without not including all the cooling and other stuff that will have to go on board, and the ruggedization that needs to happen if you want putting it in outdoor premises and so on. And now you're talking about mounting them at a 10-meter height pole top thing. And what is I see significant challenges in just tackling that particular issue. Just how do you put it up on a pole, make it stand there, and of course make it also cost effective.
Right. So that comes down to what the architecture is. So the antenna array by itself, you have physics working for you because you have smaller wavelengths. So the antenna array itself is not that dramatic an issue. Now the question is, how do you partition your RF chain? What do you leave up there? What do you bring down? Right. So that's where I think there's enough in the industry, but maybe Nokia is probably better qualified.
So we're working on this, and there's a lot of problems there. Certainly one is power, trying to get the power down on these units, and also be able to deliver the quality of the signal and the range you expect. And the other is, the antenna arrays tend to be panels, right? So what does that mean? They're sectorized. So not only that, this base station has to have multiple sectors. Each sector, then, if you have 3 of them, that's triple the power you need. And so that's one of our biggest things we're working through. Now, we expect to have worked through it and have a working small prototype within a few years. So we're fairly confident that all this can be solved. And obviously, I said the antenna arrays can be small. Relatively, you want to have lots of elements to close the link, but at say 70 gigahertz, they would be pretty small, or you may be able to use other technologies, maybe even lenses. So again, we think that the initial prototypes could be done in about 3 to 5 years on this type of thing.
Hello. My name is Wen. I'm from the University of Illinois. And this question is for the panel. And so we learn a lot about the big pictures of the millimeter wave communication. But I have a question about a very basic side. So is there any big challenges on the millimeter wave hardware, like the circuit processing, transistor use, and the passive component, something like that?
The question was, I think, about circuits and hardware and the millimeter wave RF circuitry, basically.
Yeah, I mean, I have an answer for the previous question that might apply here a little bit, so I'll use this. I mean, one of the issues I think is very interesting is spectrum, actually, spectrum harmonization. That's why it's so important to have bands that are adjacent or even ideally the same. So if you look at the moment, the situation is the FCC is allocating 28 gigahertz. In Europe, the 26.25 to 7.5 is being, is going to be the 5G pioneer band. So the question here is that, and when it comes to RF components, when it comes to the cost of modems, because RF components, they don't follow the Morse's law, so therefore this having a very fragmented kind of a millimeter wave band, that is going to have some impact on the price. Therefore, this is one of the things that is very important to see if there's a possibility for tunability of those RF components between these two specific bands, and to avoid at all costs this sort of further fragmentation of millimeter wave, because that can have some impact on thermals.
Anyone else?
So first of all, I'll give a very broad answer, which is that everything should be looked at. This is relatively new use case. Power consumption and space on the mobile unit is premium, so everything should be looked at. More specifically, I would say PA efficiency is important. Uplink continues to be a challenge, so anything that can be done to improve PA efficiencies is critical. PLL design towards lower phase noise would be particularly important. And I think one of the things that we didn't talk about much here was, it's actually very nice that the FCC is opening up so many bands, but a device manufacturer's worst nightmare is when he has to support 50 different bands. Now, the problem is further magnified, not just from the RF perspective, but also from the antenna module design. You have a fixed amount of space, and you have to share that space. So, so any kind of innovation on those fronts would be very beneficial, I think.
I just want to add one quick thing. I think there is some promising things even in the market today of some innovations on the chip front, right? I think aerospace and defense have been using these frequencies for a long time. We've got the Y-gig experience, so I think there's lots of experts on circuits here. Like Ali, I think there are opportunities there for innovation. An example is like for phased arrays. For example, I'm seeing more and more. There's innovative companies out there, traditional semiconductor companies, coming up with the right core chips to kind of do the phase. We talked about power or energy being a big problem for the analog part of these phase beam steering stuff, but there are some innovative silicon germanium chips out there that are doing this at form factor at the right time. You can actually build an array up. They're pretty suitable. And even the aerospace defense industry is now paying attention and trying to understand, it's important for their technologies to scale with cost as well, kind of lower the cost. So there is going to be some research going in there.
Hi, my name is Honimar Puyan from Boise State University. You mentioned phase noise a number of times, and so it's obvious that as you have higher carrier frequencies, you would expect the phase noise to be a problem, but I've also heard from people on the circuit side that they have solved that issue because they're now designing PLLs. So maybe you can try to at least highlight where is it that exactly within the circuitry that this higher level of phase noise comes into play. And you know, I know it's the PLL, but I mean, what is the structure? What changes? I mean, in the PLL structure, why is it that when you go to higher carrier frequencies that you see this phase noise? And the other thing I was going to ask is a second question that is different a bit is, do you see any research that is being done on the antenna side, like, you know, looking at reconfigurable antennas or different antenna structures that would help you in terms of tracking, and or also having beams that are being rated in different directions, you know, with using one RF chain to try to overcome the, you know, foliage or blockage issues?
So on the first one, I'm not an RF expert, so I cannot go into the exact details on what specific part of the PLL needs to be looked at. Generally, we don't have that much of an issue with the TCXO side of things. So it's within the VCO that we need to look at things. But it is a function of the, you know, at 28 gigahertz, it may be less of a problem, but it's also tied to the robustness of your modulation and coding scheme, right? So at the higher order modulations, it will be more sensitive. This is not to say that attacking the problem just from circuit design is the only way to go. For example, folks here talked about the 5GTF specification. There are air interface reference signals that are being introduced which allows you to track it. Now, the reason why this is important is even from the air interface design, do you need to track it on a sub-OFDM symbol basis? That will call for a different kind of reference design and a different kind of digital processing that has to make up for it. On the other hand, if the circuitry brings it down to the point where we can do common phase error estimation on a per symbol basis, that's substantially simpler to do. Your second question was regarding antenna design. So one of the things from the phone side that we think is particularly important to look at is you want to get robust 360-degree coverage regardless of the orientation of the phone. Now, this means that within a module design, you need to think about how much of that sphere you're trying to cover. Do you use just dipole arrays, a combination of dipole and patch arrays? Do you use monopoles? This comes down to, you know, your trade-off between gain and the part of the region that you're covering. Now, additionally, I talked about earlier about potentially multiple locations that you may need to place to protect yourself against hand blockage. So now you have another component here which covers the spherical space, and what is the right cost-effective method by which you can actually design these modules such that they fit within the units of space that are available, as well as give you 360-degree coverage, as well as another aspect is really polarization. Can you get polarization-based diversity or support polarization-based MIMO on the phone? So these are the aspects of antenna design, and of course, when you have multiple bands, then the problem becomes even more challenging.
Maybe I just add on the phase noise. So from what I've seen, the phase noise can be easily handled at the digital level, even after equalization, by even without any reference symbols, by doing some blind phase tracking. And as long as it's not too bad, you know, you want to keep it so that over that symbol, it's not, you know, radically changing within the symbol and not trackable. And there was also another thing was the single carrier actually allows you to track it even better, because after equalization you can go back to the time domain and then track on a smaller level where it is pretty much constant. So I think the longest phase noise doesn't really scare me. And then antenna wise, I think you pretty much covered what I was thinking. You know, something nice conformal around the mobile. You know, some new antenna designs there. Maybe even at the base having some more directivity. We don't need to scan much in elevation, especially when you have low heights. So maybe that could be taken into account. You get more directivity or something in elevation to get more gain this way, and then you want to scan more in azimuth.
Just want to add a shameless plug. Like the Nokia system, actually, like we actually brought our millimeter wave demonstration at 71 gigahertz it has a button that allows you to turn on and off phase noise correction blindly. So you can see the effect on what the phase noise correction will do. But yeah, I absolutely agree. Digital means are the way to go to kind of compensate for the analog phase noise, and it's also just a protocol aspect, right? It's all about sub-carrier spacing for OFDM, for example. You want it to be wide enough that you don't need to do these fancy ICI correction stuff that are very expensive. So I think lower cost CPE type things that Wi-Fi has been doing for years is good enough for the protocol.
I just want to make sure that my comment was understood in the right context. Whether phase noise is an issue or not is going to come down to what band you're operating at and what your subcarrier spacing is, right? So if you're talking about 60 kilohertz subcarrier spacing or 75 kilohertz subcarrier spacing the way we have it in 5GTF, and you pick the 95 gigahertz band like the person from the FCC mentioned earlier, it could be a problem, right? So broadly speaking, you are right, digital domain methods can be used to solve it, but they can be expensive, especially if you're doing sub-symbol compensation.
All right, maybe one more question before we go for break.
So this is Manisha from University of Chicago. Thanks for a great panel so far. One question, and I'd like to tie it back to the theme of this RCN, which is cooperation between industry and academia. A point that was mentioned fairly often was the need for channel modeling and understanding propagation, and we're in the infancy, we've got 10 years to do it. And one way to speed it up is to have channel modeling equipment that is more affordable. Right now, we have National Instruments and Nokia can afford it, but most of the academics in this room probably cannot. And the question I have for at least Intel and Qualcomm is, you guys have chipsets that do 11AD, that have 60 gigahertz. It's doing channel estimation on every packet that's being transmitted and received. Have you guys given any thought as to how you can take what you have and put it into something that makes channel modeling easier, more cost-effective, more available to help this effort go forward faster?
The quick, simple answer is yes, we're using it. But whether, we're in the business of commercializing that, that's not our job. I mean, companies such as, National Instruments or others, they should take that into that. But they're making money out of their machines. So
well, I want to clarify a little bit. So I think, just to be clear, like our millimeter wave system is, expensive is a relative thing, right? We actually have academics that have bought some of them, and I think they're, we want the research to proliferate. Right? We're a tools vendor at the end of the day. We're early in the technology cycle, so inherently there are some cost challenges for us building those things. So I think there is something to be said there to kind of what can we do to drive down the cost. But I think relative to our competition, it's actually fairly affordable. And also over time, we definitely have plans to drive down that cost because exactly for the reason I think we're at the infancy of it, and both for channel sounding and for just rapid prototyping of these systems. So yeah, I mean we can talk offline on how to solve that problem, I think, but it is a solvable problem over time. Yeah.
Just from my side, so mmMAGIC project will finish mid 2017, but then we are hoping to have mmMAGIC 2, which is focusing on a number of aspects, verticals, as well as operational requirements, but also channel emulators. So I think that all the measurements are going to be done, and one of the things that we are hoping to do is to come up with very good channel emulators that are going to be useful also for the research community, given that all these measurements are now have been done. So, and that also is useful for operators. So the time scale for that hopefully will be then around end 2018 and so on, and that enables, I think, the academic community to also use those.
Yeah, I think you bring up a valid point. We do have the capacity to do that. I can't say that we have done it extensively outside of the channel sounder that we have in-house. but we're not in the business of building channel sounders. So in the process of doing some prototype testing, we do collect measurements of the channel and what the delay spreads look like and things of that sort. But maybe we can talk offline about other ways to make this useful.
Well, I think with all due respect, I mean, that's you guys are, punting on this, that, we're not in the business of making channel sounders. Well, you can, one of the, so the last question here would be, one, so channel sounding is one, channel measurements and modeling is one great example where academics can help, especially if you can get sounders, and, they are being built, I think there could be some alternative sounders coming in, but what can, so one two-part question. One is, what are the places where academia can help? And two, what can industry do to facilitate that process? So even if you're not in the process of building sounders, maybe you can take a version or maybe version 1 of your sounders and share it with academics which you're not using, or where it can facilitate some research. So let's stop punting the ball and go for the touchdown here.
Okay, I thought we were at the 10-yard line about to score a touchdown, but you just called a penalty on us. Okay, so I hear you, and I think this is an area where certainly academia and industry can cooperate. So one example could be that we could talk about using some of our chipsets for building sounders in collaboration with academia, so that you have smaller form factor, lower power sounders that you could use. So we could talk about that. Yeah, there's no intention to punt.
Right, and we are in the business of doing some of that channel sounding, and I think it's great that Thiaga is here. NSF has a lot of funding for all of you. He's shaking his head. I'm kidding, but I think there is a level of I think a lot of your.
I'm going to channel Donald Trump. NI is asking a lot for their. We want NI to make money, but not that much.
Sure. No, I mean I think we kind of have to sustain the business, but think about it. Like you're all familiar with the USRP product line. So that's at a much more affordable price point.
That's not millimeter wave.
Exactly. So but you can think of any reasonable roadmap of ours would include driving the cost down to that type of form factor over time. And then so I don't want to promise any timelines or whatnot, but it is our intention. If you start off with some of the more expensive ones, over time it will go down. So.
Well, but I think this is a real question. I think if we are serious about collaborating on this research front, then I think that is what's needed. So. Joking aside, I think it's important to think about, how can we facilitate? And I think this equipment, hardware aspects are expensive and difficult, so it'll be useful to see if we can have some innovative thinking on that front. And many verticals, many things come up here. So any other questions? I think we should be breaking. Oh, there's one here, and we should be breaking after that.
Regarding the cost-effective and the large deployable broadband communications, some people are also doing investigations on the wireless optical communications. So how do you think about these two technologies? What's the advantage and disadvantage for the millimeter wave communications?
Well,
I don't want to sound too biased here, but we're having enough difficulty for, tracking in millimeter wave frequencies. Optical, as far as I know, it's more of a line of sight transmission. There are some arguments that it can also reflect, but there will be massive punishment in terms of the throughput, coverage, and so forth. can one technology replace the other one? It doesn't. But does optical have its own usage model and can, find its niche market? I'm sure it can. Maybe, communication between the vehicles. Every car has lights, and they can communicate and they can network together. But for the communications, I think we need to find some better usage models for it.
So when you say optical, do you mean like visible light communication or fiber optic? Visible light. Okay, yeah. Because on the fiber optic, I was going to answer it on the fiber optic side, but if that's not your question, I won't answer it.
No.
Yeah, wireless. Okay, yeah. But from a RF over fiber perspective, I think there are some interesting things that, like transmitting wideband signals over fiber, could be one of the innovations to kind of drive the cost down of some of this, like, front haul questions, right? Of where do I partition my analog baseband to digital baseband, and so there are some companies out there, and some of our partners are thinking about that problem. So there are innovative things I think that we can do there to drive some of that cost down for fiber optic type of.
I think there are some other hardware-related synergies there too, but I think that may be some topic for the breakout too. So actually, before we split for the coffee break and then 11:30, the first set of poster sessions, we have 3 breakouts, for hardware, signal processing and communication and networking. So I just want to get a rough. You guys are free to move around, of course, every over an hour, but a rough breakdown of how many people are interested in different. So hardware, show of hands. All right. And then communication and signal processing. That's about the same. And then networking. That's okay. So I think we'll have to, there'll be one here, either communication and signal processing or hardware, and one next door, and then one in a third room. So we'll have that information later. Okay, so let's thank you. Let's thank our panelists for sharing information. We have a coffee break. I think coffee is next door, and session 1 will start at 11:30. So if you're in that, please set up your post in this room.